Hello, this is Mr. Wakefield once again, and we're back at the final section of Chapter 10, looking at systems of nonlinear equations. This expression should look familiar to you. Back in the beginning of Chapter 3, let me show you a quick view of that. Back at the beginning of Chapter 3, we had systems of linear equations, and now we have systems of nonlinear equations. So it's going to be very similar, but there's a little bit of a difference. When we have systems of linear equations, they call it that. Obviously, the big difference here is the word linear versus the word nonlinear, okay? When we saw them before, when we had two equations, and we'll just have two equations today. We won't have those ones that have three equations or anything like that. Just the two equations today. But when we had two linear equations before, why do we call them that? It's because, again, a linear equation is when both sides of the equation is a normal polynomial. This is a monomial here, and this is a couple of monomials being added together. Okay, so those are both polynomials then, as we define polynomials throughout the semester. This is the same right here on the second equation, and so they're both linear, and that's why it's a system of linear equations. As we go on into today, you can see here that this one anyway right here is not linear because, pardon me, I forgot to mention one thing here. Not only do they need to be polynomials on both sides, but also the highest degree of any term needs to be 1. Okay, in other words, x to the first would make this a degree 1 term. Y to the first makes this a degree 1 term. No variable at all makes this a degree 0 term. So you got degree 1, degree 1, degree 0, highest degree is 1, right? When it's a highest degree of 1 with a polynomial on both sides, again, that's linear. But what makes this system different? Even though this equation on top here fits that linear description I just mentioned, degree 1, degree 1, degree 0, this one down here does not. Okay, because it has a degree 2 term right there. If you have an x squared or a y squared in your fraction or in your equation, you guys, it is definitely not a linear equation, no matter what. And so, therefore, because you have an equation that is not linear, it cannot be a linear system. And so we just call it a nonlinear system whenever there's either one equation or in some cases both equations are not linear. Okay, so this is not linear because you have an equation that is not linear. Okay, so even if you have another equation that is linear, it doesn't matter. Okay, if one of them is not linear, then the whole thing is a nonlinear system, as we call it. And so the stuff that we do is still mainly the same. The substitution method is still the same as it was before for the most part. Okay, there's some other little guidelines we need to follow and we need to be careful of. One thing that we need to do, and we were reminded of this in Chapter 5 briefly, we did a problem at the very end of Chapter 5 in Section 5.7 where you had a linear equation and a nonlinear equation. This is nonlinear because this is actually a degree 2 term right here. When you got two different variables in your term, you got to add the exponents to figure out the degree. But anyway, that's not important right now. What's important is that this is a nonlinear system. And what we learned is that usually it's best that when you have a linear equation and a nonlinear equation, it's best to substitute, if you're going to do the substitution method, which they ask us to do here in this current section. You want to plug the linear one into the nonlinear one. It's usually easier that way instead of going the other way around. So if you get a linear equation and a nonlinear equation in your system, I would recommend that you plug the linear one into the nonlinear one. Now, what do we mean by that? What do we mean by plugging in a linear into a nonlinear? Again, with the substitution method, we learned that before you plug one equation into another, you got to first of all, as we saw here back in Chapter 3, you got to first of all get the variable by itself in that equation that you're going to plug in, and then you plug it into the other equation. Okay, so we're going to do that same thing here, and you can see I did that here. I got this from the second equation right here. I got the y by itself, and then I plugged it into the first one there. So I'm going to do that same thing here. If I get the y by itself in the linear equation, and I can do that by subtracting the 2x over to the other side. Okay, and I would get this right here, wouldn't I? Okay. And we've seen anytime you have, just a review here, when you have an equation with more than one variable in it, the way to get one of the variables by itself, if it's a linear equation, is just to move all the terms that don't have that variable in it that you're trying to get by itself, which would be y right here. Get all the other terms over to the other side by adding or subtracting them over, assuming there's no parentheses to clear out first. And then you divide out. But I don't need to divide out here because the y is already by itself. So just a little review there. So then I then plug it into the other equation like I just talked about. So you can see here I plug the y from the first equation into the y from the second equation. And very similar to what we've done in the past when we do the substitution method. Okay, and what it creates is it creates a one variable equation. You don't have a y in here, just an x only. Okay, so it's a one variable equation. Now what's different though compared to the systems we usually did in the past is that it's not a linear equation, though. It's a quadratic equation because of the x squared. Okay, and so because it's a quadratic equation, and it doesn't tell us how we need to solve the quadratic equation. In other words, it's our choice which method we're going to use. Remember, there's 4 different methods for solving a quadratic equation. So let me give you just a little bit of review on that. When we do have the choice of what kind of method we want to use to solve the quadratic equation, remember we said that if you have an x squared with no parentheses or anything, but just an x squared, but then an x in the x term in your equation as well, then usually you move all the terms to one side and you try to factor it. And if it doesn't factor, you can do the quadratic formula, but if it does, even better. Okay, that's again when you have an x squared, but you also have an x term separately from that. You can see that we have that here, don't we? We have an x squared and we have a couple of x terms here. So it looks like it's one of those types of equations where you're going to move all the terms to one side and try to factor it. Now, since I'm going to try to factor it, remember to keep the x squared positive. That's what we typically do when we want to use the factoring method, as we've said before. So I'm going to move all these over by adding or subtracting them over. That gives me 0 here. Like that. And then you try to factor that. Well, that looks like a Berry method type of problem right there. Okay. Where you have a product of 12 and you have a sum of 8. What two numbers are going to give you a product of 12 and a sum of 8? Okay. Wouldn't that be 6 and 2? Okay. And so that means what? That means that we're going to get x plus 6 and x plus 2. And you don't need to do the last step of the Berry method because the two brackets are already they don't have a GCF in them to factor out. So I set those equal to 0. Again, all the same stuff we normally do in the factoring method for solving quadratics. We originally learned this method in 5.7 if you ever want to review that a little bit more. But what we end up getting here, as you can see here, is 2 answers. Okay, when we solved systems before, you always ended up getting only one answer when you solve for a particular individual variable. Okay, this time we got 2, so it's a little bit of a different thing going on. So what you do if you get 2 answers, which you oftentimes will in these problems, is I need you to look at them both separately. So you can see I'm doing that up here. I'm putting -6 and -2 in 2 separate categories right here. And what you're going to do is you're going to do the same thing that you did before when you did the substitution method. You're going to take the answer that you got. Let's just look at -6 for first of all. We'll look at that one first. But you're going to take -6 and you're going to plug it back into any equation that has both variables in it. Okay. We did that back in chapter 3. After we solved for a variable, we went back and plugged it into an equation that had both variables in it. Preferably the one where the other variable that you haven't solved for yet is by itself. Okay, but you don't have to do that one. You could do any equation that has both variables in it. So let's do that same thing here. I'll pick the variable. I'll pick the equation that has the other variable in it by itself. right there, where you get it by itself in the first step before you plug it into the other equation. That's the equation I'm talking about. If I plug -6 into that, what do I get? There it is right there. So then I need to figure out what this is equal to. Okay, there's no variable there, so just do order of operations on that side of the equal sign, since there's no variable on that side. And we get -5 plus 12 is 7. Okay, and so what does this mean? This means that -6 pairs up with 7. Okay, you have to pair those up. Okay, -6 is not going to pair up with whatever y value you get as an answer over here with the -2. Now what's going to happen is -6, whatever answer you get, that has to be a pair. So you need to pair that up. You need to put that in as an ordered pair to show me that it's those two numbers that go together. Okay, so let's see what -2 goes together with. If I plug in -2 into that same equation, this one right here, okay, -5 minus 6 times, or pardon me, minus 2 times, and then I plug in -2, I get -5 plus 4 is -1. And so that means that -2 for x pairs up with -1 for y. And so again, whatever answer you get for -2, you got to pair that up with it. Whatever answer you get for -6, you got to pair that up. Okay, so that you're showing me that, in other words, you can't just circle the two x's and the two y's, all right, and just say, hey, these are all 4 of my answers here. You can't do that because this -6 and the -1 don't go together. -2 and 7 don't go together. So if you just circle all 4 of these answers here, these two up here and these two here, I'm not going to know what numbers are paired up with what other numbers. And so you need to pair them up like this. Okay? And one last thing we need to do, this is very rare, but it could happen, and so you don't want this to cause you to get the wrong answer. As we've talked about in the past with fraction equations, you guys, and radical equations, and also some of the logarithmic equations, all right, we said that it was mandatory to check your answers. All right, when you're solving a system of nonlinear equations, you will sometimes get extra solutions, answers that are not solutions. All right, you'll always get all the good answers if you use the methods I'm showing you here, but sometimes you get some bad ones added on to that. And so you need to check your answers. These two answers right here, how do we check to make sure that they truly are the real answers? Okay. In order to be a solution to a system, it has to make both of the equations true, okay, that the system comprises of. It comprises of these two equations. Okay. Now you don't need to check them both because see how the last equation that I plugged into at the very end of the problem, that equation came from the first equation. Okay. We wouldn't have gotten these two answers unless it agreed with this equation that was on the last step. So you don't need to check the equation that you used on the last step, which came from the first equation. It's equivalent to that one. So therefore, you just need to plug into the second equation, and if it works for that one, then you can be certain that it works for both. Okay, so let me try that. I'm going to check. So plug in the 7 in. I'm going to plug in this one first. Actually, let me write that down, just so you can see which one I'm doing here. I'm going to check this one first. And so I'm going to plug in 7 into y. And I'm going to plug in -6 into the x part. Is this true or not? Okay, you check both sides of the equation to see if they're equal to the same thing. On the right-hand side, do order of operations there because there's no variables here. If you do that, you can see that we get exponents first, then multiplication. So we're going to get -30 plus -36, same thing as -36. And you can see here that this is indeed going to be equal to 7. Okay, that's going to work. How about checking the other one, though? If I check, the other one was -2, -1. If I check that one in that same equation, we get what? We get -1 for y, and we get -2 squared plus 6 times -2 plus 7. Okay, and so that gives me what? That gives me exponents first, then multiplication. And is it true that 4 minus 12 plus 7, is that equal to -1? Yes, it is. Okay, it is. Just like this one was true. So it's very rare that you get a false answer, but it could happen. All right, and so that's why we check it. All right. So that is number 1 right there, or problem A rather. These are the 2 answers we get. Occasionally you get even more than 2 answers. Anyway, let's move on to the next one. The next one, again here, you see that this is a linear equation, polynomials on both sides. Highest degree is 1, x to the first, y to the first, those are degree 1 terms. This is degree 0 because there's no variable. These ones up here, even though they initially look like, even though this equation initially looks linear because you just see x and y, if I remember, when you figure out what the degree is, the highest degree of an equation, you got to ask yourself, what would it be if I cleared out those parentheses? Okay, because it has to be a polynomial on both sides in order to figure out the highest degree, and it's not really a polynomial if the parentheses are there. Now, this does not mean that you literally have to get rid of these parentheses, but you just have to ask yourself, what if I did get rid of the parentheses? What then would be the highest degree? Well, you can see here that if I were to multiply this out, and again, you don't have to. As you'll see here, it's not going to be important yet. But if you multiply this out, you're going to get an x squared term in there, aren't you? Okay, if you multiply out those 2 brackets. And so for that reason, I know that this equation is not linear, but yet this one is. And as we said in the last problem, if you've got a linear equation and if you've got a nonlinear equation, okay, go ahead and plug the linear one into the nonlinear one. So how are we going to do that? Well, the easiest way to do it, just like in the last problem, is find the first of all, find the equation that you're going to get a variable by itself in, and it's this one because it's linear. But take the variable that's easiest to get by itself. Since there's just a -y right here, this is the easiest one because you don't have to worry about dividing out, okay? And I know that because if I move the y over to the other side, okay, and then if I move the 3 over with the 2x, okay, and you're allowed to do that. You don't, just because you're getting a variable by itself doesn't mean you have to keep it on the same side. You can move it over if you want to change the sign of it. Okay, so I move that over, and then I move over the 3, and then you can see that the y is now completely by itself. So the goal is still the same, even if you move the variable that you want to solve for. The goal is to get it on one side by itself, okay, without that y on the other side. All right, and you're allowed to, as long as there's no parentheses in that equation, you can add or subtract terms however you want in order to make that happen. And if you still end up with a number in front of the y, then you can divide that out still, but we didn't, so that's fine. Okay, now, how do I solve this now that I got the variable by itself? Well, again, you now plug it into the other equation, just like we always do after we get the variable by itself when we're doing the substitution method, as the directions tell us to do here. So let's take the other equation. I'm going to plug that in. So I'm going to actually plug in 2x minus 3 right here into the y right there. And then I'm going to solve that resulting equation. Now, if you have like terms that can be combined inside of a parenthesis, go ahead and do that. That's going to make it a lot easier here. And if I combine like terms right there, I get 2x minus 2. 2x minus 2. Because what we're going to do next... and I know we've seen this before, you guys. You might be thinking this, but back in Chapter 8, we learned that when you have a quadratic equation, the bracket squared. You usually try to get it by itself if it's not already. The difference with this problem, though, is that there's two brackets being squared, so you don't want to do that. So if you have two brackets being squared, first thing you want to do, you guys, is clear out those parentheses, all right? And we do that in doing the same thing I just implied earlier. Multiply this out, okay? What would that be equal to here if I did that? Okay, if I multiply that out using the same thing we have always done with multiplying out brackets like we did in chapter 5, okay, where you multiply out the parentheses. Back in 5.2 we learned about that. Again, let me just give you a visual of that real quick here. How you multiply out brackets, all right? You've got the 4 different multiplications right there, all right? When you got 2 terms in each bracket, that's what I'm talking about here. And that's what we're doing here. So we get x squared minus x plus 1. Bring down that plus right there. And then do the same thing with 2x minus 2. Multiply that out. Okay, and we get what there? We get 4x squared minus 4x plus 4. Okay. All right, and so we got that right there. If I then, after I distribute out, I usually combine like terms before I decide what to do next, and then it'll kind of shed some light on what I have here. If I combine like terms, I get 5x squared, but then the x terms become negative 10x, like that. And since I have, once again, just like in the last problem, since I have an x squared, okay, and it's not anything bigger than that, just x squared, not x to the third, that means that you're going to realize it's a quadratic equation. And since it has x squared, but it also has x in it, okay, then that means that you're going to move all the terms to one side. But when I do that, though, what happens? The 5's cancel. But that's okay, though. All right, we can still factor it, because what do we always look for first when we factor, you guys? We always look for the GCF. And there is one here, and that's really going to help us. So always look for that GCF first. So if it looks unusual, like something you don't normally factor in an equation, don't panic, all right? Try to look for the GCF first, and maybe that'll kind of shed some light on what to do. You can see here that if I do that, I just get a green single term factor here and a red multiple term factor. And so we've seen that before, okay? If you've just got a single term and then a bracket, and if that bracket's prime, and I know that it is prime, by the way, because if you've got 2 terms in one of your factors, one of your bracket factors that has 2 terms in it, if it's got 2 terms with x to the first power, that's automatically prime. So that means when we what? That we set those 2 factors equal to 0. Okay, and that gives me what? If I divide out the 5, right? Oh, I'm sorry, that came off the screen. Excuse me. Let me start over there. There we go. So I brought this up. I've set the 2 factors equal to 0. I divided out the 5 right here, and then I can add the 2 over to the other side on this one. And once again, just like in the last problem, it gives you 2 answers. Okay, let me move this over a little bit so we have some room. I'm not changing the answers, don't worry. Okay, I'm just moving it over a little bit so I have some room to work. But again, just like in the last problem, I've got 2 answers. And so now what I do, just like in the last problem, is I go back to the equation where I got the variable by itself in step 1 before I plugged it into the other equation, and I just plug it into that, okay, to figure out what the other variable is equal to. So this one will be 2 times 0 minus 3 equal to y. And then the other equation will be 2 times 2 minus 3 equal to y. And then that tells you what the other variable is going to be equal to. So 2 times 0 minus 3, that's 0 minus 3. 0 minus 3 is negative 3. Okay. 2 times 2 is 4. 4 minus 3 is 1. And so that means that y is equal to 1 right there. What do we got to do here at the end? Just like we did in the last problem over here, we need to pair them up. Okay, don't just circle the 4 different answers you found, 2x and 2y. You got to pair them up. So 0 and -3 go together, pair those up, and -2 pairs up with +1. All right, now before you circle that, officially we need to check our answers here. Since I got, remember I said you don't need to check the equation that was the last equation that you used on the last step right here. Last equation I used on the last step, that came from the second equation here originally. So you don't need to check that one when you check your answers at the very end of the problem. You just got to check the one that was not involved in the very last step right here. So that would be the first one here. Again, the 2x minus y equal to 3 is, that's where this equation came from when you got the y by itself. And since you used that in the last step, that's why you don't have to use that. You don't have to check that one. You just check the other one. Okay, so what do we got here? If I check 0, -3, okay, if I plug in 0 here and do order of operations, that gives me -1 squared. 0 minus 1 is -1 squared plus, let me bring down the plus, and then I plug in -3, -3 plus 1, and I'm going ahead and getting started here. I'm doing the parentheses here first. -3 plus 1 is -2, square that. Is that equal to 5, yes or no? It is equal to 5 because if I do order of operations, I get 1 plus 4 right there, which as we know is equal to 5. And so this first order pair is definitely true. And as I get ready to check the next order pair, I just realized that this is a misprint right here from what I just wrote a few minutes ago. It should say 2, 1, not -2, 1. So I apologize if that threw you off there. You're probably wondering why I didn't fix that before. It is +2, 1, and that's what we're going to check. Okay, and so 2, 1 is going to be, when I plug in 2, I get 2 minus 1 here, which is 1 squared, plus what? Plus 1 plus 1 squared, that's 2 squared. And is that equal to 5? It sure is, okay? Because again, you get 1 plus 4 equal to 5. All right, so both of these are true. Both of them are true here, just like they were in the last problem, but you just got to check to make sure, because there are those rare instances, you guys, where you could run into a bad answer. Okay, now what we're going to do here is I'd like you to try number 1 right now. We're going to skip number 2. You don't need to do that one. That one's a little bit different than the others, but we don't need to worry about that. If we do number 1, we'll be fine. But in number 1, you might be wondering, is it okay if I know you've been saying, Mr. Wakefield, that we should do the linear one first and plug it into the nonlinear. But is it okay if I take either x squared or y squared right here and get the x or y by itself using one of these two terms up here? Definitely do not do that, you guys, because if you ever take an x squared or a y squared, when you have a 2-variable equation, I'm not talking about a 1-variable equation like this, where you have just a 1 variable and you take the x squared and you get the x by itself down here. That's different. But when you have 2 variables, you guys, and you try to get one of the variables by itself, when that variable is being squared, that's not a good idea. Because then you're going to end up, here's what's going to happen. You're going to still end up with the double square root like we did here in this problem that had just the 1 variable. But because the current problem has 2 variables in it, you're going to end up with a variable underneath your radical. Okay, instead of just having like a 5 underneath there, like right here, which is not bad, you can have a variable underneath there, and you're actually going to be making the problem more complicated than it originally was, and therefore you're going to actually be getting further away from getting to the final answer than you were before. And we definitely don't want that to happen. We want to get closer to the final answer, not further away from it. So the lesson is that if you have a 2-variable equation and you have a variable being squared, do not get that variable by itself. That is not a good idea, and that's one of the reasons why we want to choose the linear equation to get the variable by itself first, and then we plug it into the nonlinear equation. All right, so I'd like you to try that right now. Hit the play button when you're done. And just a reminder, just like in the last problem, if you've got a negative y and you want to get the y by itself, you can move the y over and then move the 5 over here, and that'll get the y by itself just like that. It's a pretty easy way to do it. And then you would plug that equation into the other one. Okay, it's similar to this one. It's a little bit different because you don't have the big brackets, but otherwise it's very similar to that one. So give it a shot, hit the play button, and then we'll take a look at the answer. All right, let's take a look at number 1 here. Again, we're going to start out with the linear equation first. I get the y by itself just in the same way I talked about. If I then plug that into the other equation, what's it going to look like? It's going to look like this right here. Again, use a parenthesis whenever you plug into a variable, unless you're sure that it doesn't make any difference. Usually it does make a difference though. And so you can see here I put a parenthesis in the place of y here, and then I plug the 3x minus 5 into it, just like you always do when you're doing the substitution method. And then just like in the last problem that we did, if you've got a parenthesis with 2 terms in it, again, you might be thinking, hey, can we do the square root property where we get the bracket squared by itself? No, you can't do that here, because if you did that, that would mean that you'd have to move the x squared over to the other side, and you can't do that bracket squared thing with the square root property like we did. Let me show you here, like we did. Let me just get that back up here on the screen here real briefly. We were allowed to use the square root property when you get a bracket squared by itself if there is no variable on the other side. And you can see there's no variable here. However, if I move over that x squared, there's going to be a variable on the other side. So the only choice, the only realistic choice we have here is to distribute out these parentheses if you're not going to do the square root property. We always distribute out the parentheses in a quadratic equation, which I know that this is because of the x squared, unless you're going to do the square root property, So that's why I'm going to multiply these out. And if I do that, I get these 4 terms right here that I highlighted right there with the big bracket on the top. And you can see here then that we can now combine like terms before we decide what to do. And I actually did a couple of steps in one here. You don't have to do that. But I combined like terms. I ended up with a 25 and a 5. I then went ahead and moved the 5 over to the other side because I knew that it was one of those problems where you wanted to move all the terms to one side. Because I was going to be able to factor it next. And so I did that, and that's what it's going to end up looking like. Now notice, please, that before you get into the Berry method here, which is the obvious choice, remember there's a GCF right there, and it's 10. And that's going to make the Berry method easier to do anyway. So I factor out the 10. I then do the Berry method. I get x minus 2 and x minus 1. So I've got a total of 3 factors. And when you've got a term times a bracket as you're factoring on the other side of the 0 here, you then what? You then set those 3 things equal to 0 in the factoring method. If you set 10 equal to 0, that's no solution, because 10 equal to 0 is a false statement with no variables, okay? And that means no solution, as we've seen before. But these 2 brackets give you a couple of answers, and it would be x equal to 2 and x equal to 1 if you set those equal to 0 and then you solve for those equations. So once again, just like in the previous 2 problems, we have what? We have a couple of answers, okay? Zoom out here so you can see it. There we go. Those 2 answers are going to be x equal to 2 and x equal to 1 up here. And so let's start out with x equal to 2. And again, I plug it back into the equation where I got the variable by itself in step 1. That's the easiest way to do it. So for that one, I got y equal to 1. For the other one, I got y equal to negative 2. And so I pair those things up. And I get 2 comma 1 and 1 comma negative 2. And those are my 2 answers. Just go ahead and check those by checking it in the equation that you did not use in the last step here, which was the first equation. And doing that, you can see I did that down here, and in both cases I got a true statement again. 2 squared plus 1 squared, 1 squared plus negative 2 squared. Both of those things are equal to 5. Again, I plug the numbers into here. Each pair one at a time. Okay, so you can see I checked the two ordered pairs separately here. Okay, so that's why I circled both of those answers. And that is the substitution method, you guys. Okay, let's take a look at the back side of your worksheet there. And in the back side, they talk about the elimination method. Again, the elimination method is going to be similar to the way it was before. So let's talk about that. Also known as the addition method, by the way. And so let's just take a quick look back to Chapter 3 once again. When we learned about the substitution method, this is 3.1 once again, where you want to be able to add the equations together and eliminate a variable. It doesn't matter which variable you eliminate, as long as you eliminate one out of the two variables, you can then get a one variable equation to solve. Just like we get when we do the substitution method. When you substitute, you get a one variable equation. When you eliminate, same thing, you get a one variable equation that you can solve. All right, so we're going to do the elimination method here, and it's in a very similar fashion. Okay, we want to be able to add the equations together in order to eliminate a variable. So what was our goal in Chapter 3? Our goal was to make the a pair of terms opposites of each other so that they would cancel. All right, and usually we would have to multiply by either one equation or, in some cases, both equations in order to make what? In order to make the terms opposites of each other so that a variable would cancel out. Okay. Well, you'll notice here in the first problem that if we add it right now without even having to multiply by anything, the y's will cancel out already. How come? It's because we have opposite coefficients here, don't we? -1, +1. Just like over here where we had +15, -15, or -5, +5. As long as it's the same number but opposite sign, and that's the case here, -1, +1, then we know that it's going to cancel when we add them together, assuming that they're like terms, and these are like terms. Otherwise, you can't even combine them, okay? But if you can combine them and they have opposite coefficients, same number, opposite sign, then they will cancel. -1 and +1 will cancel. So when I combine these together, I get what? I get 8x squared. The y's cancel, of course. And then 4 plus 4 is 8. So what does this lead to? This leads to, again, a one variable equation. And as we reviewed from Chapter 8, you guys, when you have a quadratic equation, which this brand new equation is, if it's got just x squared in it, you guys, but no x term at all, just x squared, unlike this one down here where it had x squared and also x, and we've seen a number of those equations already in this current worksheet. But if you've got just x squared, what do? You pretend like that variable, just like I did in Chapter 8 right here, you pretend like that variable is, and also its exponent. Put a red box around that. You don't have to use a red box, but just put a box around it. Even if you do that in your head, you don't have to write down the box. But imagine that there's a box around that, and imagine that that's its own separate variable. Like, for example, what if you had 8y equal to 8 instead of 8x squared equal to 8? So that box is like a variable. Sorry, that came off the screen there. And so 8x squared equal to 8, just like 8y equal to 8. We talked about this in Chapter 8 here, when we imagined that the box was like a variable. You imagine getting the variable by itself. How would you do that here in this current problem? You divide out the 8, and you get y equal to 1. The point is that you do the same thing here in the actual problem. You do the same step. You divide out the 8, and then just like y would be equal to 1 up here, you're now going to have x squared equal to 1. X squared equal to 1. And so that's definitely an equation I can solve. Now, when you get x squared by itself, as long as there's not a variable on the other side, just like x squared equal to 5 in this problem we did in Chapter 8, okay, if you've got x squared by itself, not 3x squared or 8x squared, no, x squared by itself, then you can do the double square root, as long as there's not a variable on the other side. Well, that's exactly what we got here. We've got x squared by itself. The variable is not on the other side, so we can do the double square root. And if your square roots are perfect squares underneath, like 1 or 4 or 9 or something like that. Go ahead and simplify that radical right now, evaluate it, and figure out what it's equal to, and we get 1 and negative 1. And once again, just like we've seen in the previous 3 problems, we have 2 answers for the first variable. Okay. So again, we do them separately here, and what we do is we, just like we did with the elimination method in chapter 3, you guys, again, you go back and you plug into any equation that you want as long as it has both variables in it. It's your choice. Okay, and so I'll go ahead and pick this one, just to pick one. So I plug in x into that. I'll do the other one in a minute here, the negative 1. Always when you plug something into a polynomial equation, like this one is, because it's a polynomial on both sides, you first of all figure out what the term is equal to that you plugged into. Okay, remember exponents come before multiplication, so this would be 4 times 1, wouldn't it? 1 squared is 1. And 4 times 1 is 4. So once again, we got another one of these quadratic equations that is similar to the chapter 8 one that we keep on looking at here, where you've got just the variable being squared, but you don't have the variable without the exponent. In other words, in this problem, you have the y squared, but you don't have the y. If you've got the y squared, but you don't have the y, again, you can do the quadratic, the square root property again, just like we did with this equation right here. All right. Pretend like that's a variable right there. Pretend like, say that that's a z right there. If you had 4 plus z equal to 4, wouldn't you get the z by itself by subtracting the 4 over? And that's important because that means then that I can then move the 4 over here in the actual problem that we're doing. Okay. You just do the same step that you would do if it was just a normal variable, talking about the y squared. Now that you have the y squared by itself with no variable on the other side, just like I had x squared by itself with no variable on the other side, you do the double square root. So the double square root here would be plus or minus square root of 0. Plus or minus square root of 0. But isn't that just equal to 0, you guys? Because isn't it true that the square root of 0 is 0? I can write it down up here if you having trouble seeing that. Plus or minus the square root of 0. Square root of 0 is 0, and we know that 0 is the same number whether it's positive or negative. Positive 0 and negative 0 are just one single number, 0. And so that's why I'm saying this whole answer here is just one number, 0. Okay, so plus or minus square root of 0 is just the same thing as that one number, 0. And so once again, we end up with a pair. The 1 pairs up with 0. I'll check that answer in a moment. Let's go ahead and do the negative 1 now. If I plug in the negative 1, can you see here that it's going to be the same answer? If you don't see that yet, let me prove it to you here. If I plug in the negative 1, though, isn't it going to give me the same term here? And I need to figure out what that term is equal to that I plugged into first, as I just mentioned. Negative 1 squared is 1. 1 times 4 is 4. And so as you can see here, that leads to the same exact equation that we had over here. So since it's the same equation, shouldn't it be the same answer? Y equal to 0? Okay, no use in doing the work all over again, right? If we already solved the same equation just a minute ago, all right, we don't need to do it again. We already know what the answer is going to be. So that means that negative 1 also pairs up with y equal to 0. And once again, we've got 2 answers right there. Okay. And so what we need to do next then, as usual, is to, I shouldn't circle this, but I already know that they're going to work. Don't normally circle them, okay? Check your answers. And I can always erase it if somehow they weren't true, but I already know that they're going to be true because I've done this problem before. But yeah, check. Don't forget to check. So where did I get that last step from? That last step that the equation I used in the last step there came from the second equation. That means that when you check your answers, you just need to check it in the first one here. So I'm going to check the 1, 0 first. If I plug it into the first equation, that's this one. Okay, I get this right here. Is this true right here? Well, if you do order of operations on both sides, which again I'm going to do because there's no variables, okay, and I need to figure out whether or not it's true, I end up getting 4 minus 0 equal to 4. And yes, that's true. If I check the other one here, which is what, negative 1, 0? Can you see that it would be the same result? If I plug in negative 1 right here along with 0, wouldn't it just be 4 minus 0 again? Because the only difference is that you're going to square the negative 1, but it's still going to be 4 times positive 1 when you do that. Okay, so it's the same answer. It's the same equation that you get when you try to figure out if it's true or not. And so I'm just going to point to that same one. No use in writing it down again. I already know that's going to happen. And so both of these are going to be true. Okay, and therefore now I can confidently circle those two answers, knowing that they are both going to be true. Okay, next one here. Problem D. Again, they want us to do the elimination method, so they want us to either cancel out the x's or the y's. Here's the problem, though. You can't cancel the y's. The reason why you can't cancel the y's is because when you do the elimination method, you cannot multiply. Remember I said that, and I know you've done this before, but remember when you do the elimination method, you got to multiply sometimes by an equation in order to get the numbers to be opposites of each other. We talked about that a few minutes ago. But you're not allowed to multiply by a variable, just by constant numbers. Otherwise, I won't get into all the theory behind it, but it's going to potentially mess things up if you try to multiply by a variable. And so because of that, I cannot take two numbers take two terms that aren't like terms and eliminate that variable because they're not like terms. And if they're not like terms, you can't combine them. And if you can't combine them, you guys, then they can't cancel out. These two terms are not going to cancel each other out. Even if you make this negative 2 and positive 2, that's still not going to cancel out because they're not like terms. You can't cancel them if they're not like terms when you're actually adding them together, adding the two equations together. And so, therefore, since you're only allowed to multiply by constant numbers, there's no way you can change the y and the y squared. It's still going to stay that way, y and y squared. So the only choice that you have then, which is fine, but the only choice you have is to eliminate the x squareds instead. Since they're currently the same coefficient, positive 1 and positive 1 right here in front, if I multiply the first equation by negative 1, okay, that would get the job done, wouldn't it? Okay, again, the goal here is to make them opposites of each other. And the way you multiply by an equation, as long as there's no parentheses and it's a normal polynomial equation, is you just distribute to each term here. Keep the equal sign in the same place. Just like I did here with the negative 5. Let's do that right now with the negative 1, like this. Okay. What equation do I get? I get negative x squared plus 2y equal to negative 8. The other equation is going to stay the same because I wanted the x squares to be able to cancel, and they will now because they're opposite coefficients now, negative 1 and positive 1. So let's go ahead and add the equations together now. The x squareds will cancel. We get 2y plus y squared equal to positive 8. Okay, so here we go again. We've got a quadratic equation because of the y squared. I know it's quadratic. And it's another one of those equations where you got the variable being squared, but you also got the variable somewhere else, taken to the first power. X squared and x, same thing as y squared and y. Okay, same idea. So you want to be able to, because it's got y squared and it's also got y, we want to move all the terms to one side and then try to factor it. Okay. Now I want to keep the y squared positive when I move all the terms to one side like I normally do. And so that means I want to move the 8 over. And put it in this order right here when you move the 8 over. So if I subtract the 8 over, it's going to be negative 8, isn't it? If I subtract the 8 over, but put it in this order, because whenever you have the y squared and the y and the constant term, you want it in that order. You want the y squared, like I said, to be positive, and we did that. So now we can do the Berry method as long as it's in that order and the y squared is positive. All right, and we get what? Wouldn't that be y plus 4 and y minus 2 if you do the Berry method? Again, review that in section 5.4 if you need to, the Berry method I'm talking about, but that's what it comes out to be. We then set those two factors equal to 0, okay, because it's we're done factoring that now. All right, it doesn't factor anymore. We set those equal to 0. And what two answers do we get there? We get y equal to negative 4 or what? Y equal to positive 2. Okay. And so once again, just like in the last problem, and just like in all the problems we've been doing so far, we get the two answers, split them up into two parts, and then figure out what the other variable is equal to for each part. Again, when you do the elimination method, you could pick any of these equations you want to plug into. I'll go ahead and pick the first one there. Just as long as it has both variables in it, you can pick either equation you want. Any equation you want. So there's the first one there. Again, figure out what the term is equal to that you plugged into. And if you plug into a negative term and it's not the first term there, there's a term in front of it, remember that is plus negative 2y. So when you figure out what that term's equal to, remember that that is plus negative 2 times negative 4. So that would be plus positive 8, wouldn't it? In other words, don't just write down 8, write down plus 8, because you're adding negative 2 times negative 4. And so, like we've seen a lot of times here in the last few minutes, all right, you've got an x squared in your equation. We saw that over here with the y squared. You got an x squared in your equation, but you don't have an x in there. And so that means you're going to treat the x squared like it's just a normal variable, like a z or something like that. And again, what would you do if it was z plus 8 equal to 8? Okay. What would you do if it was z plus 8 equal to 8? Wouldn't you move the 8 over in order to get the z by itself? And so it's the same thing with the box here for the x squared. You move the 8 over, you get x squared equal to 0, and oh, we just did that, didn't we? We learned about what happens when you get the variable squared by itself and it's equal to 0. That means that officially the answer is plus or minus square root of 0. But as we just reasoned a few minutes ago, that's the same thing as just saying that one number 0 right there. Okay, so the only difference is that it's an x this time instead of a y, but that doesn't matter. All right, that's just a letter. Okay, we're trying to solve for that letter, so it's going to be that same answer, x equal to 0. So that means that negative 4 pairs up with 0. Oh, I'm sorry, I got that backwards. Remember, the x always comes first when you write out your ordered pair. So 0, comma, negative 4. And then what happens when I plug in y equal to 2? Let's see. If you plug in y equal to 2, plus negative 2 times 2 is plus negative 4. That's the same thing as minus 4, so I'll just write down minus 4 right there. But you figure out what that term is equal to that you plugged into first. Then you, again, treat the x squared like it was a normal variable. You got to get by itself because there's not another variable in the problem besides the x squared. So you add the 4 over to the other side. You get x squared equal to 12. And since I got x squared by itself, with a constant on the other side, no variable over there, that means you can do the double square root. So that gives me two answers, doesn't it? This is the first time this has happened, and it won't be the last time, but it's the first time. Where one of these two numbers here actually gives you two answers. What do you do in that case? And let me go ahead and simplify this radical first here. Square root of 12, as we learned in chapter 7, you can factor a 4 out of that. Okay. That would be square root of 4 times square root of 3, and then the square root of 4 becomes a 2, doesn't it? So square root of 12, again, a lot of review going on here in this section, isn't it? Okay, we're seeing a lot of stuff that we've seen in the past. But that's good, though, as we get closer to the final anyway. So square root of 12 becomes this, and it ultimately becomes 2 square root of 3. So we get 2 square root of 3 and negative 2 square root of 3. But what do we do when we have two answers like that? What we do is we take the y equal to 2, and we have two ordered pairs. One that goes, that pairs up the y equal to 2 with the positive 2 square root of 3, and then one that pairs up the y equal to 2 up here with the negative 2 square root of 3, like that. Okay, so we have a total of 3 possible answers here. Okay, let me write that a little bit bigger. Okay, but that's what you do when you're on that last step and you plug in a variable, plug a number into a variable to figure out what the other variable is. If you get 2 answers, then that means it's going to create two more ordered pairs right there. So we end up with a total of 3 here. All right. Checking our answer, we would check it in the second equation up here because of the fact that the last step here involved the first equation, where I plugged stuff into the first equation on the last step right there. So you just have to check the second equation. If I check the second equation, I get what? I get 0 squared plus negative 4 squared equal to 16. That is definitely true. Doing order of operations, I get 0 plus 16 equal to 16. Okay. And then on the other one, the other ones I should say, it doesn't matter if it's 2 square root of 3 or negative 2 square root of 3. No matter which one of those you plug in, it's going to be the same. I'll show you here. But let me just plug in the positive one first, and then I'll talk about that more. But plugging that in, remember you guys, 2 square root of 3 is the same thing as square root of 12. And as you guys know, when you square a square root, as long as it's not a negative number underneath it or something like that, if you square a square root, it's just going to be equal to the number underneath the square root. So square root of 12 squared is going to be equal to 12. Because this is really square root of 12, and square root of 12 squared is 12. In other words, the square and the square root cancel each other out if there's just a square root only underneath there. Okay, so you can't just eliminate the square root here and say 2 times 3. That's not how it works, okay? It's just when there's just a square root only, they're not a 2. So that's why I use the 12 here. Let me write that down off to the side. I squared this instead because it's easier than squaring when you have the 2 there. But it's the same thing because square root of 12 and 2 square root of 3 are the same number. And so either way, you're going to end up getting 12, though. 12 plus 4 is 16. That's true. And then if you plug in the negative 2 square root of 3, which is the same thing as what? It's the same thing as negative square root of 12. As you guys know, when you square a negative, it's the same thing as you're going to get the same answers when you square a positive, as long as it's not like an imaginary number or something. Okay. So negative square root of 12, when you square that, it's going to be equal to 12 also. A negative number, as long as it's not imaginary, when you square it, it's going to be positive. And so the fact that you made this negative square root of 12, it's still going to end up being 12 when you square it. And so therefore, it's going to be the same equation, and therefore it's going to be true once again. Okay, so that is problem D right there. All right, so go ahead and please try these last 2 problems right here. I got to go ahead and circle this here first, though. There we go. And so go ahead and try these last 2 problems right here. Just a little bit of a heads up here. Notice that I can multiply, not that this is the only way to do it, okay? You could multiply by both equations to make these cancel each other out like we did in Chapter 3. Or how about if you just multiply this one by negative 2 right here? Negative 1 times negative 2 would be positive 2, and then that would cancel with the negative 2. So just a suggestion right there. And then here, this one's similar to problem C up here, where you've got 2 that are the same coefficient. And so if I multiply one of them by negative 1, it would then give me negative 1y and positive 1y. That'll get the job done as well. Okay, so please try 3 and 4. Hit the play button when you're done, and we'll see how the answers come out. All right, looking at number 3 right here. I went ahead and, as I suggested just a moment ago, I multiply the bottom one here by -2. That'll make the equations look like this right here. The -2 and the 2 would then cancel out the y squareds when you add the equations together. But what resulting equation do I get? Okay, I get -1x squared equal to -1. But I need to solve that equation. Remember, when you have an x squared in your equation, but you don't have an x in there, and it's quadratic, which it is because it's x squared, because it's got an x squared and it's quadratic for sure, you need to get that by itself. And then you do the double square root thing that we've done so many times. So I divide out the -1 right there. It's just like if you had a -1 times a variable here, -1 times x squared, same thing. Treat the box like it's a variable. Get it by itself by dividing out the -1, and we get this right here. We then do the double square root. It's going to be positive square root of 1 or negative square root of 1. Okay, both of those are, the square root is equal to 1 there. Okay, it's a perfect square, so just to figure out that it's equal to 1 there. And it gives you 2 answers again. Just like we keep on seeing here in all these problems. You get the 2 answers, okay, and then you what? And then you plug both of them in separately, but you plug them both into either equation, or actually any equation you want as long as it's got both variables in it. Any equation you want. I went in and picked the very first equation at the very top of the problem. I plugged it into that. And you can see here on the first one, figuring out what the term is equal to that I plugged into, doing that first like we always do, we end up getting this equation right here. And once again, you've got the variable being squared, but that's it. Okay, the variable's not anywhere else. It's just a y squared with no y anywhere else. That means that we treat the y squared like it's a variable. We get it by itself in the same normal way. So I subtract the 3 over, and then I divide out the -2, and I get y squared equal to 4. Okay, then doing the double square root after we get the y squared by itself, as long as there's no variable over here, you're allowed to do that. You get what here? You get y equal to plus or minus square root of 4, which results in 2 answers, just like we saw in the last problem. Okay, sometimes you get 2 answers down here when you plug it into the other variable, and the 2 answers are 2 and -2. Square root of 4 gives you, with the plus and minus, it gives you 2 and -2, doesn't it? And so what did we do in that last problem when we got 2 answers here at the very bottom? We paired them both up, and so that leads to 2 possible answers here, 1, 2 and 1, -2. Because the 1 for x pairs up with both 2 and -2 over here. Now, if I plug in -1 instead of 1, excuse me, let me fix that there. If I plug in 1 instead of, -1 instead of 1 right here, it results in the same equation, because when you square -1, it's the same thing as squaring +1. It should give you the same result. And so no use in solving the same equation again. You can see that these 2 equations right here side by side are exactly the same. And so I know it's going to give me the same answer down here when I get y by itself, 2 and -2. And therefore, it results in 2 and -2 down at the bottom again. And so I pair up x equal to -1 with those 2 possible answers, and I get a total of 4 answers. Oh man, do I got to check all 4 of those answers? Yeah, you do, but it's not as hard as it sounds, because what equation do we need to check it with? Well, this last step here, I used the first equation in the original, right? I used the first equation when I did that very last step here, so I don't need to check that one. That means I checked the other one. And when I check the other one, remember you guys, it doesn't matter. Let me go ahead and zoom back in now. It doesn't matter whether you, when you're squaring something, it doesn't matter whether it's +1 or -1. That's why I put the plus or minus in here. me zoom in a little bit closer so you can see that. It doesn't matter if I plug in positive 1 or negative 1. Normally, you don't plug in a plus or minus. normally you plug in the positive 1 and the negative 1 separate. But we know that it does not matter whether you plug in positive 1 or negative 1. It's going to be the same answer. Positive 1 squared is 1. Negative 1 squared is also 1. So that's the point I'm making right here when I plug in the plus and minus. It's going to be the same either way. All right, and same thing with plus or minus 2. Since you're squaring, it's going to be the same result either way. And since our 4 answers are just a combination of 1s and 2s, some of them positive, pairing up with negatives and so on, all different combinations of that, all of those 4 answers are going to give you the same result right here. 2 times 1 minus 4 equal to negative 2. So even if you did all 4 of the ordered pairs and you check them all individually, one at a time, it will always give you the same equation in all 4 cases. So no use in writing them all down separately. Okay, we know it's all going to come out that way. And we know that it's true here because 2 minus 4 is negative 2. Same thing happens down here, okay? 1 and negative 1, 2 and negative 2. That's what basically your 4 answers are consisting of. No matter which combination of those you plug in, because you're squaring both the x and the y, it's always going to come out as 3 times 1 and 2 times 4 for that first equation. And not that you even need, I don't even know why I did this actually. You didn't even need to plug this in because that actually came from the last equation that we used on the last step. And like I said, you don't need to check that. For some reason I wrote that down. I'm not sure why. You can check this, but you don't have to because again, it's the equation that we used on the last step. So as I've been telling you all along here, you don't need to check that. But I went ahead and did that. But you just needed to check this first one here. Okay, I won't cross this out because it doesn't hurt to check it. But it's just not necessary to do to check the equation that you already used on the last step, just before you found the 4 ordered pairs. Okay, but the other one was true, and so that's why I went ahead and circled all 4 of these answers right here, and this problem is now done. Okay, so let's go to the last one here. If I multiply the first one by negative 1 like I suggested a few minutes ago, that will make the y and negative y opposites of each other so that when I add the equations together, I get this right here. Okay, and by the way, if you had multiplied the other equation by negative 1 instead, the resulting equation you would get would look a little bit different, but I promise you it'll ultimately come out as the same answer in the very end. So don't worry if it looks a little bit different than what my equation looks like at the moment. Now, what you want to do, since this is since this has got an x squared in it, but it also has an x in it, is like I've been talking about this morning here, reviewing from chapter 8, we want to move all the terms to one side. Okay, put it in this order if it's got all 3 of these terms there. Make sure the x squared is positive. Okay, so put it on the side that'll make x squared positive. You then do the Berry method. We then set the factors equal to 0 here. Okay, x minus 3 equal to 0, x plus 1 equal to 0. That leads to these 2 answers here, as we learned about in the factoring chapter. Okay. And like always, after you get your 2 answers for the first variable, we then plug it into any equation you want that has both variables in it. I went ahead and picked the second equation at the very top, the 2x plus y equal to 1, and I plugged it into that one. Okay, and then it gave me these 2 answers right here. The reason why I circled them is because I've already checked the answer. All right, but let me show you how I checked it. Since I used the second equation in the original system to do the last step, I just need to check the first equation then. And so I plugged in these 2 ordered pairs into the first equation, and you can see that they both come out as true. This is 9 plus negative 5 equal to 4. That's true. And this is 1 plus 3 equal to 4. That is also true. Okay, so that concludes systems of nonlinear equations. Okay, please please follow the directions that they give you here. As you gain more experience with this, you can actually choose the method you want, but for now, follow the directions. It does say here to use the elimination method on these 4 problems. On the problems on the front, it says to use substitution. Please do, again, do that not only because the directions say so, but because in some cases anyway, in many cases, if you try to do the other method, it's going to be a lot harder. Okay, so there's a reason for that beyond just following the directions. So, and on the final exam also, it will say you need to use either the elimination method or in another problem, it might say you need to use the substitution method. So watch out for that and make sure to follow your directions. Okay. So that concludes section 10.5. You have a good day and take care, and we'll see you back in section 11.1, which is the beginning of the last chapter, rather, of Math 71.